Hi, my name is Neuhaus. I'm a research scientist at IHMC, and I'm going to talk about our experience with the DARPA Robotics Challenge trials. IHMC is a small research institute in Pensacola, Florida. We're about 100 people total, and we're a nonprofit basically doing contract and grant-based research, kind of soft money stuff. That's our team at the trials. We're all looking pretty happy. I don't remember what day that was. But you can see it's a big team. We had about 20, we used up all of our passes, 25, and then some. Our team is made up of a range of levels of education, starting with high school students. We work closely with the local high school and getting their pre-engineering students to come and do an internship, all the way to people with doctorate degrees. So this is kind of my pitch to any professors that have graduate students or any graduate students out there that are looking for a 3 to 6 month or longer opportunity to come work with us. We're really open. So 3 is about the minimum. 6 is a great length of time to come and stay with us, work with us, maybe get a paper out of it, see how we operate. So if you're interested, you can contact me after, or find us online and write us an email. This is our team from the Virtual Robotics Challenge. You can see there's some common faces, but it was kind of a high turnover around between the 2 projects. So we do take people in and try to get them up to speed pretty quick. There's a range of universities that we get students from, or degrees that people have come from, and a range of countries. So we look for we take international students as well. No problems with ITAR, and we work with J1 and H1 visas and all that stuff. So our approach to the DRC was it was a multifaceted project. It wasn't just algorithm development or software. Kind of had to do everything: operator interface, software engineering practices, and software-hardware integration. And I'll go over each of those. So our first was control algorithm. We use a capturability-based approach to looking at maintaining balance and walking. So the model is modeling a legged system as an inverted pendulum with a point mass at the top, maintaining a fixed height. And when you do that, the dynamics become first-order linear. So you can now control where the center of mass, how to move the center of mass in a pretty controllable way. The blue is the instantaneous capture point, where if you put your foot right there, you come to a complete rest based on your dynamics currently. But of course, you can never step exactly instantaneously. The shaded circle represents the ring of end-step capture points, where you can now take a step. And so we have to kind of model about how long it takes to take an average step, and then place our foot, depending on where your instantaneous capture point is relative to where your foot is. You get different shapes of your end-step capture regions. Here it is in our simulation environment. So we use our own simulator called Simulation Construction Set. And then we have a lot of different ways of visualizing objects. In this view, it's a little fast. I'll slow it down and zoom in. So the blue is our desired instantaneous capture point, and the yellow is our actual. So you can see we're doing pretty good tracking. We try to make a visualization for everything we're trying to control. So you see a lot of balls and arrows and trajectories. And this is kind of one of our key ways of doing development. So when someone's developing some new controller, some new calculator, or whatever tool it is, and they have a problem, the first thing we'll ask is, well, do you have a way to visualize what you're trying to accomplish? And if you don't, we'll push to get a visualization so that you can see their, the coordinate frames, all these kinds of things that make debugging easier. The next is, once we have our instantaneous capture point motion, we use a momentum-based whole body control to generate ultimately the joint torques. So we have the available contacts. For the VRC, we used hands as well in order to get in and out of the car. For the DRC, we didn't use the hands as balance, in the balance equation, so we just used the feet. So the available contacts for the DRC was just the feet. The instantaneous capture point dynamics come into the rate of change in momentum. We use a QP solver and come up with the kind of idealized torques, the wrenches and the joint accelerations. We then calculate the inverse dynamics and come up with the applied joint torques. So we operate in a torque control mode, which is pretty important for our algorithm. Here it is just an example of our whole body control getting into a car. In fact, we When we drove the car, we had to hold on with a hand and one foot on the ground. We didn't sit on the seat due to some of the instability in the simulator. So it was pretty important that we had a good way to control the joints in that case. The operator interface, we use a coactive design approach to designing operator interface. So, you know, we try not to neglect any area of this project, because you neglect one area and it can kind of cause problems in the ultimate challenge. So what it's not just interface design. It's not saying, hey, just give me a panel that has a button here so I can click joint angles or some visualizer. It's not just deciding what functions to automate. And automation, there's been some touch on it in this talk today, and it's something we also work with as to, you know, how much to automate. I'll get into a little bit more of that later on. That's determining what level of autonomy. And what it is really about looking at the human-machine teamwork and looking at what the relationship is and what the interdependence, and really understanding how the two can work together. So one of the questions as you're designing a user interface is, well, and you have automation, is what's the robot doing? And you click the button and now it's moving, but it didn't move in exactly the way you want it to. What's it doing? We try and ensure that there's transparency. There's some visualization. Again, even just in our control algorithms, in our user interface as well, there's a way to see into the internal workings of what's going on. Or why did the robot do that? You know, what was it doing? What state is it in? We have explainability. What's the robot going to do next? So hopefully there's an understanding of what state the robot is, what it's planning to do, and that's predictability, and how can we get the robot to do what we need, and directability. And does autonomy add value? And that's kind of the critical question that we're going to be working on in our future research for the finals, is how much autonomy, and looking at it cost benefit. So does it off-weigh some of the load on the operator, but at what expense? Is it reliable enough, and are we able to then predict what's going to happen next? Here's a shot of our operator interface. On the left is the camera. It's a combined, the stereo vision plus the fisheye cameras, and on the right is our virtual model that gets populated by our point cloud map. So we can now adjust. You see on the left the sliders tilting the head up and down, so we're basically sending commands to the controller that goes through the network shaper that says move the head up and down. We can now populate or add to the view you'll see in a second a virtual model. So we're going to add a virtual door, and once we have a door in place, we can now adjust it to match the point cloud map and then operate on that door. One thing, the way we operated, the way we ran at the trials and in the virtual challenges, we now have scripts to interact with the door. We have a series of poses, of footsteps that will go and open the door. If our localization is off, we can adjust the model of where the door is relative to all the point clouds, and the scripts automatically adjust to stay with that object. So it's a pretty robust way to operate, kind of have a nice balance between autonomy and teleoperation. So like opening a door, we'll have a series of hand poses that the operator can then play back those hand poses, modify a single hand pose, and then execute a hand pose or execute a sequence of poses. Here we're just altering what the hand pose should be. We'll put a valve out. You can see there might be some error between the camera view and the virtual model view. But we do the augmented reality so you can actually see where some of the objects are being placed. We partnered with Atlassian for the trials, and we use their tools significantly. So they have a ton of tools that we use, because this is also a software engineering project. One little code bug can, cause your whole performance to degrade to zero. So we do continuous integration. So every time someone makes a code check-in, we run over 2,000 unit tests that verify that our code is still working. And if one of those tests fail, we'll all get an email, and the person who's assigned to kind of babysit Bamboo will then be responsible for doing that fix. You can't actually check in code while the Bamboo is not compiled, while their single test is failing. In addition, we also run tests, end-to-end tests. So these tests take longer to run. We don't run them on a continuous basis. We run them every night. And they're tests to make sure that the robot can still walk or climb or manipulate. And then in the morning, we'll see these videos. If one of them doesn't play, we'll know something's wrong. It also will cause Bamboo to fail. So it's a significant way of reducing errors in your performance. And we saw that we kind of learned our lesson with the Little Dog program way back a number of years ago to really be rigorous about our code and compile and check in, because one error can also cause some serious problems. And you might test it on one condition but not realize that you just broke functionality on another case unless you test kind of everything. We do an agile project management, so every 2 weeks we kind of do an iteration. We determine what are the user stories that we're going to take into this 2-week iteration. We vote on it. We assign story points, which are kind of an abstract way of determining effort. And then we only work on those items for that 2 weeks. And then every 2 weeks we kind of reshift what our focus is or work on new projects. So it's a nice way of really keeping our group on track, and we track our progress with Jira, which is another Atlassian product. So as the other teams hinted out, we had about 4 months from the day the robot arrived. That also included moving to a new space. Here's our first robot lab with pretty low ceilings, and it's only about 1,500 square feet. We later moved in mid-September to an 8,000 square foot space. So there was a lot to deal with. Not only do you have to get the software right, but you also have to integrate your software into the hardware. And we had to deal with back joint failing, IMU issues, torque at the knee, limited torque at the knee or failing knee torques, and you'll see, collapsing. So all these are problems that you have to deal with when you're going from, in simulation everything's great. You don't model all the nonlinearities, you don't model the saturations and all the noise issues. We didn't use any of the canned built-in routines of Boss Dynamics control. We basically commanded the joints at the pretty low level. Because of the stiction, the arms had a significant amount of stiction. We had to change from a typical just force control to combining it, as one of the other presenters mentioned, with a position and velocity kind of integrator, so that we would maintain trajectories, but at the expense of compliance. So our arms were not very compliant. Sensor calibration, so you might have your point cloud map, but you might not match up your augmented objects in the two views. And so we just had to, that was another area that we had to get right in order to be able to perform, as well as making sure that your hand was where you thought it was actually operating. Sensor noise was a huge one since we're using the low level. The main sources were backlash, link elasticity, communication latency, and sensor noise. Try and get all that displayed itself as the shakies. So we reduced gains, added filters, compensators, and modeled the elasticity in the system. And then we tested a lot. Tested on springy platforms over various objects, because you might be great on flat ground, but the wood might introduce a resonance that might take the event, get into your controller and cause an instability. And the problem with feedback control is you can't separate where your instability is coming from. We do unit testing on software. We also do unit testing on hardware. We saw the foot slipping in hardware. So you take a step, and just as you're about to do weight acceptance, the foot would slip. Instead of just solving it in hardware, we'd go back to the simulation, reproduce this behavior in simulation by changing the way we interact with the ground, or the ground contact model, until we see the same effect. Then we account for it in our control algorithm, so it didn't become a problem, create a unit test that would capture with that controller on and off, and then we go back to the hardware and verify that it works. So it was a pretty complete way of ensuring that any hardware issues we saw were taken care of in our controller, and verifying that that control functionality wasn't eliminated or reduced by another fix. Someone else might be developing a controller that takes it into account, so we would have now a unit test that took care of that. What do we need to get ready? So this kind of gives you a little bit of insight into our team and what it was like leading up to the trials.
The update of how we're doing. What's the date? It's the 22nd of October, right? We got less than 2 months to go. So now the main challenge is getting that software that worked in the virtual challenge work on real robot. Some things are working really well, some things are working horribly. It's been very frustrating because our software works so well in the virtual robotics challenge, and now it's not quite working on a real robot for multiple reasons.
We're a day away from packing up our robot to ship it off to the trials, and we've been working tirelessly right up to the last minute. The amount of work we've done in the past 2 months and even the past 2 weeks has been tremendous. This preparation has included more than just trying to develop on the robot and to adapt our software, but also to try and experience what it's like to operate a robot in these environments. And so we've put in a tremendous amount of time and energy into recreating the trials as they're going to be by building these test structures and setting up valves and tools and ramps and blocks and even things that aren't in the spec, and just trying to be able to develop a system that's robust to any sort of real-world scenario we could find ourselves in.
So what we did is we'd have mock trials, and as we got closer and closer, we'd schedule these mock trials, which was a dedicated day to running through the different tasks. We might do 3 different tasks that day, freeze our code the night before, lock it down, no changes, and then run. We'd have a chief score, we'd have a timekeeper, run with a 30-minute time window and interventions and all that to make sure that we accounted for every kind of possibility so there weren't any surprises. So we might run the doors, then you can see we're set up to run the different tasks, sequentially. And that was a really important part. Not only do we test our software, JUnit test at the small end, we also test our whole process end to end in the way that we expect it to be on the day of the competition. So what was it like at the trials? Well, a lot of you were there, but for those of you who weren't, it was pretty exciting. We tried to have a lot of fun. There was one of our other projects, the Hex Runner. But it was a lot of logistics of getting all of your gear there. There was also a lot of excitement. This is right after the terrain task, which was our first day and probably the one that we were most nervous about. He was our main operator, John. She ran almost all of our tasks in just an excellent way. Has a great insight into the robot. Probably, part of our success was due to, a really talented operator, but as well as all the other parts. So how did we do on the tasks? Well, I won't go through all of the videos, but I'll just kind of highlight some of them. One thing that was pretty exciting was having this being a public event. The crowd really, made us feel like we're doing something pretty amazing. And then as we're walking across, you see the crowd start to build up on the right and extend on the right as we get further and further along in the terrain tasks, and then we're throwing out t-shirts and getting the crowd riled up. So the operator, even though we could relay back to the operator, subtask 1 complete, 2 complete, he could hear the crowd cheering and get that feedback as well. I don't know if that was accounted for when DARPA thought about the rules. The door task is probably our most interesting task. You can see the operator view here. So one question we always get is, well, when the robot's standing there, what's going on? What's going behind the scenes? And so the operator has a co-pilot, and he's populating the scene with the virtual objects, going through the different scripting objects, making sure and double checking that as he executes that command, we'll do a preview of an arm motion before sending it down to the robot. So we send a command down about every, if we're doing a sequence of moves, about every 10 seconds or 20 seconds. We'll send only single pose on the hand, so we'll move the hand to a pose and send down the next one, and then send down the next one, and each one checking to make sure that we didn't lose localization. footsteps, we can send, a whole string of footsteps will only take, especially on the rougher terrain, about 2 footsteps, then reevaluate, localize. Because our user interface is pretty flexible and we're able to kind of be adaptable, we handled the wind pretty well. It just took a lot of extra time. You see we're about 20 minutes and we're still going through the second door. So things got pretty tight for the operator. We had about 5 minutes left to go through the third door. And so he just, at that point, we went into kind of high risk mode, and he's just basically hitting next step with very little checking. And so that's kind of where we can proceed, with a greater level of autonomy. Is if we feel comfortable with the localization, we can now stitch these steps together and just send them down as a full packet, and just let the robot just execute on that and do its own possibly localization checking. Here we're about 5 seconds, so we crossed the third door with about 10 seconds to go. So it's pretty exciting. We came in second in the trials. So development for the finals, we're looking at proven walking. We're going to use the hand contacts for whole body control. It's going to be necessary for the ladder and getting in and out of the car, or getting out of the car. Improved localization, we're inspired by Morris's work at MIT, or challenged by it. We think that it's a great piece of work, and we're looking to do similar state estimation. Multiple instruction, as I said, trying to stitch together sequences rather than just do a single one at a time. Multiple simultaneous operators, so maybe have one person looking at the terrain and scoring it and determining the footsteps while the other person is actually doing the instantaneous planning. And then we also have to be able to get up from a fall and safely fall. That's it.
Questions?
Yeah.
So it looked like you guys were very focused on specific, training for specific tasks. Did you guys run the same exact software throughout, or did you have sort of
Same
frozen
software.
pieces of software you knew worked?
Same software. So unlike Little Dog, where we did have specific executions for the different terrains, and we'd freeze it. We'd get one part working, like the steps. We'd freeze it, lock it, and that way we know nothing would break it because we'd load that jar file when we encounter that terrain. In this case, it was same code for everything. We can switch modes, so we can switch into like a car ingress mode for the VRC, which we didn't need in the DRC, where we now allow available contacts to be greater than just the feet. And we wouldn't use the instantaneous capture point for balancing at that point. Yeah.
So for getting up after a fall, Boston Dynamics was going to develop some primitives to help with that. Are you using those, or are you
We'll
starting fresh?
probably start fresh. We were able to, in the virtual challenge, get up from a fall through a sequence of kind of pre-programmed body motions. We'll probably start at that as a starting point. But with hardware, it'll be interesting because sliding on the ground might cause problems, or you might scoop up dirt depending on what we're on. So we'll just have to see. We haven't gotten there yet.
I think most teams are probably pushing back on that until we get the new arms. I mean,
Yeah, it'll change significantly once the arms
on the robot in general.
change. Yeah.
Gil had a question
Okay.
about what you plan to share.
We're pretty open, especially if people come and work with us. Our code base is open up to where we have NDAs signed with different code bases. But we're looking to open up more of our algorithms we'll be announcing that in the next probably couple weeks. But we like to share. We're part of an academic institution, and that's kind of our model, is making sure that our developments don't just stay internally, but help the community out.
Great. All right, thank you, Peter, one more time. All right, and our next speaker is Peter Neuhaus. He's filling in for Nick Bradford, who couldn't be here for personal reasons, and so he's going to